Hi everyone, my name is Jordan Meyet from the Material Characterization Lab at Penn State. Today I will be discussing the coupling of thermogravimetric analysis and FTIR spectroscopy with mass spectrometry for evolved gas analysis. Evolved gas analysis is a powerful technique for the characterization of material as they undergo thermal change. While standard TGA or in situ FTIR helps you understand the weight loss or the change in functional group of a material as a function of temperature and atmosphere, respectively, coupling this technique with mass spectrometry for evolved gas analysis allows you to pinpoint the exact molecular species released during decomposition and correlate them to the change observed on the material. This hyphenated technique provides complementary information helping us answer the question, what is in the gas phase? A mass spectrometer is an analytical instrument used to identify and quantify molecules based on their mass-to-charge ratio. MS system operates under vacuum, where the gaseous molecules are transferred to the ionization chamber through a capillary. The ion source converts the neutral molecule into ion and generates fragments of the parent molecule. After being sorted by their mass ratio using a mass filter, they are detected and displayed in a mass spectrum in the form of intensity of ion as a function of mass ratio. While chemical ionization using reactive gas exists, evolved gas analysis often use an electron ionization, which causes extensive fragmentation of the molecule, resulting often in the absence of the molecular ion. Understanding the fragmentation pattern is crucial as they determine how we interpret the mass spectra and identify gas phase species. Evolved gas analysis using mass spectrometry is perfectly suited for permanent gas like hydrogen, carbon monoxide, methane, carbon dioxide, water, oxygen, and nitrogen, or light gas such as hydrocarbon C1 to C3 and light solvents. Medium and heavy gases present more challenge, and gases described as non-volatile with a boiling point above 250 degrees are not suitable for evolved gas analysis using mass spectrometry due to their potential condensation in the transferring capillary line. Acquisition can be performed either using selected ion monitoring, which is a fast acquisition when the mass-to-charge ratio of the gas of interest are known, or it can also be done using multiple ion detection, a slower method which scans a range of mass-to-charge ratio and is used for partially unknown products. To select the appropriate mass-to-charge ratio to analyze, the fragmentation pattern of the molecule of interest needs to be known. In addition, knowing the fragmentation pattern of gases evolved allows to avoid monitoring overlapping signals. A common example is carbon monoxide and nitrogen that have both a molecular ion mass ratio of 28. Okay, now let's look at a practical example, the decomposition of calcium oxalate monohydrate. Its thermal decomposition is well known and has been extensively studied. The first step is a dehydration. The second step involves the conversion of the oxalate to carbonate, leading to the release of carbon monoxide and carbon dioxide. The final step at high temperature corresponds to the conversion of the carbonate into oxide by releasing carbon dioxide. Using TGA-MS, we can track the release of water by looking at the mass-to-charge ratio of 18 and carbon dioxide by monitoring the mass-to-charge ratio 44 as the sample is heated. We can see on the graph enclosed the three steps correlated to the gas released during their respective decomposition. However, in this analysis, carbon monoxide cannot be analyzed since the signal overlaps with nitrogen, which was used as a carrier gas. Overall, the evolved gas analysis experiment provides insight into the decomposition pathway and stoichiometry of calcium oxalate monohydrate. FTIR coupled with mass spectrometry can complement the TGA-MS data and vice versa by providing a molecular level information of the material at a given temperature. Diffuse reflectance FTIR spectra of calcium oxalate monohydrate during the thermal treatment reveal change in the functional group of the material, such as the decrease of the OH vibration mode and CO stretch during decomposition. By integrating the FTIR peak corresponding to the OH vibration and CO stretching group, we can correlate their disappearance with the release of water and carbon dioxide respectively. This dual approach yields a more complete picture of the decomposition process of calcium oxalate monohydrate. Another potential application of TGA-MS is for monitoring gas adsorption such as carbon dioxide uptake on hydrothalcite material. TGA-MS allows to track mass change and MS signal variation for carbon dioxide, oxygen, and water during the calcination step, purging, and adsorption step. Switching the carrier gas and monitoring their corresponding MS signal allows to confirm the addition or depletion of the specific gas. The mass gain after the introduction of carbon dioxide allows to quantify the adsorption capacity of the material, demonstrating the value of TGA-MS for studying gas-solid interaction. When we look at the thermal decomposition of 6,6 nylon, it presents a single decomposition step. But when we coupled with MS signal, we can see a complex mixture of evolved gas. MS analysis from 1 to 100 atomic units during the decomposition reveal a complex fragmentation of the polymer backbone and side chain. The large amount of fragments and poor knowledge of the decomposition pathway make the analysis of this material extremely challenging. MS analysis of the thermal decomposition allows us to identify key fragments based on the chemical nature of the material and knowledge of basic volatile molecule. For example, at mass 17, this mass corresponds to ammonia, the mass 18 corresponds to water, and the mass 44 corresponds to carbon dioxide. The remaining fragments are more complex to interpret and corresponds to C2H3+ at 27, C3H5+ at 41, C3H3O+ at 55, and finally cyclopentanone at 84. While this ion could correspond to a variety of volatiles molecules, having knowledge of the literature allows us to make this assignment. In the reference enclosed, the assignment was only possible due to advanced cryo-GC-MS technique and isotope labeling experiments. To conclude, mass spectrometry coupling for evolved gas analysis is best suited for confirming and correlating suspected gas phase composition rather than identifying unknown. For that, it is essential to know your sample and expected outgassing product to avoid heavy gaseous products. Literature and prior data are essential to help guide the selection of suitable mass-to-charge ratio and interpretation of the results. Finally, always work with small amount of sample when uncertain. Thank you very much for watching this video.